Perfect. So, hello everyone. I'm very happy to introduce Bartosz Gren from University of Warsaw, who will talk us today about a classification of algebraic tangles. Please, you can start.
Thank you, Paola. So as Paola introduced me, I'm Bartosz Gren from University of Warsaw, and I want to show you my work, which was done under supervision of Joanna Sułkowska and Boštjan Gabrowczak. So my talk is about classification of algebraic tangles. So I want to start by asking a question: why to classify the tangles? So we can say that the journey started from the Conway's idea how to classify knots. So his idea was to create graphs built from 4-degree vertices, and in place of these 4-degree vertices, insert the tangled strands, which he called the tangles. The tangles follow some simple arithmetic operations, so they can be added. So every two tangles connected by two vertices can be represented as another tangle. Therefore, there is a restriction on a minimal unique set of such graphs where tangles can be inserted. So Conway, using these graphs, which he called polyhedra, he managed to classify all knots up to 11 crossings and links up to 10 crossings. So these are these polyhedrons he used. And these circles with L's, letter L inside, represents a tangle. So by inserting tangles inside these polyhedrons, he classified knots and links, as I said, although he does not classify tangles. Later, Moriucci classified handcuffs and theta curves in a similar way. And he classified tangles, handcuffs, and theta curves up to the 7 crossings. So our idea was to classify more complicated structures, and also to extend the classification of handcuffs and theta curves for more than 7 crossings. So we actually managed to classify tangles, of course. And we happen to classify tangles up to 14 crossings. So, but actually, what was the motivation behind the classification of tangles? So we are dealing with proteins, and proteins are biological polymers, which from the topological point of view, they are like simple strands, but they can have extra bonds, a lot of different kind of bonds, but the strongest one, the cysteine bonds, which are like regular bonds across the strand, change the topology of the protein. So naturally, theta curves, handcuffs, and more complicated structures arise in this structure. So this was our motivation to to attack this problem. So now I want to introduce you to types of tangles, starting from the basic ones, and actually how we define a tangle. So from the intuitive point of view, we can just say that tangles are part of knot diagram, as I said during creation of when I talked about creation of knots during Conway's method. But from the more formal point of view, a two-tangle, because we are talking about tangles with two strands, is an embedding of two arcs plus any number of circles into a free ball. And these endpoints of these open arcs lie on the boundary of the ball. And such sphere we call a Conway sphere. And there are four basic tangles which are building blocks for more complicated tangles. And these are, as you see over here, tangle 0, infinity, 1, and -1. And also, as I said before, tangles can be added together, but also we can introduce the operation of multiplication. So they differ by this, that the first factor is rotated around, I'm sorry, it's not rotated, is reflected along the diagonal P, which we call a principal diagonal. When I will call the diagonal, I will refer to this P diagonal. And while the summation is more intuitive, multiplication is often more useful. Both of them are useful, but every summation can be represented as multiplication, but contrary is not true. You can imagine that F tangle here on the graph is a tangle 0 actually. Then we have just the operation of multiplication by 0, R0. And this operation cannot be represented by a simple summation. I want to focus your attention that the multiplication is not the order matters here. Multiplication is not commutative. And from basic tangles, we can create more complicated tangles, starting from integral tangles, which are just the sum of 1 and -1 tangles. And intuitively, we can just assign a number, integer number, to each integral tangle. And using these integral tangles, we can create rational tangles, which are represented. Those are these tangles, which can be represented as a multiplication of integral tangles. And we can look at these integral and rational tangles from the point of view that we can take a 0 tangle. Now I will drop the sphere. We can take the 0 tangle and rotate the endpoints around x-axis. So we can switch north, east end with southeast end by a rotation, and it will give us 1 or -1 tangle. And we can do the same on the left side. And just by rotating the left or right side, we will get some integral tangle. And we can do the same thing we can rotate also north or south points. And these operations are enough to create any rational tangle. So rational tangles have intuitive physical interpretation. Of course, these operations are more than enough, because also we can twist the whole tangle. So rotation of the east points can be also represented as rotation of west points, and vice versa. Here is an example of some complicated rational tangle, which is created by these operations I told you, rotation of the right, left side, and top bottom. And when you look at the diagram on the left, I marked a rectangle. So if you rotate this rectangle vertically, no, I'm sorry, horizontally. If we rotate this rectangle horizontally, then we can move the integral tangle on the left to the right. And such operation we call a twist. The same thing we can do with a second diagram. So there is a marked rectangle. And over there, we can rotate this part of a diagram around vertical axis. And it will simplify our rectangle even more. But this is not the end of our possibilities. We can also rotate the rectangle on the third diagram around the diagonal axis. So around the diagonal north, west, south, east. And such operation we call flight. And this one is the hardest to rotate in mind. Rational tangles are especially interesting because there is a perfect invariant of them, which is not very common thing in a knot theory to have a perfect invariant of something. By perfect invariant, I mean that if we have two tangles with the same value of invariant, we can be sure that these are the same tangles, that they are isotopic. This invariant is a fraction. So to every rational tangle, we can assign a fraction, which is calculated in the way as you see. So if we have a rational tangle by using continued fraction formula, we can calculate tangle fraction. So as you see on the bottom, it's not easy to see how to perform these operations, how to rotate these rectangles in your mind. But we can just calculate the fraction of each of these tangles. All of these fractions are equal to 2/7, and we know that these tangles are just isotopic. So this invariant was proposed by Conway in 1970, but the proof of this invariant came later, that the invariant is perfect, by Burde and by Kaufman later, easier to follow proof. And these rational tangles naturally fraction of these rational tangles naturally create a classification of rational tangles. to every fraction. With every fraction, there is some rational tangle connected. But of course, rational tangles are not only possible algebraic tangles. By algebraic tangles, I mean all tangles which can be built from basic tangles by addition and multiplication. So also we can add and multiply rational tangles together. And then we get more complicated tangles, which are harder to study. But I show you here some non-rational tangles, which we wanted to study, but there are also non-rational tangles, which we didn't want to study because they are in some way, we can say pathological. We can also say that they are complex per analogia to prime knots and complex knots. So as you see here, these complex tangles are knotted in a way that this knotted part can be moved along a strand. So moves, isotopy preserving moves, which can be applied to such tangle are simply non-local. If you look at the diagram on the very bottom end, you can see a quite complicated tangle with ring on it. And you can imagine this ring can be moved along the strand to any place on this strand, which makes classification much harder. So we didn't want to classify all tangles which have which have a subtangle starting from 0, because these are these complex tangles. So after excluding of these complex tangles, we've chosen these 5 moves to be our basis for classification. So we treat tangles as isotopic if they are related to each other by any of these 5 moves or composition of these 5 moves. These moves, of course, follow strictly from Reidemeister moves or are compositions of them. If you look at the left top part of the slide, it's simply first and second Reidemeister move. But on the right side and at the bottom, twist and flips are compositions of second and third Reidemeister move, and ring move 2 is a composition of second and third Reidemeister move. So our assumption is that 2 tangles are isotopic if they are related by these moves. As I mentioned, multiplication and every summation can be represented as multiplication. And also I said that order of multiplication matters. So if we add here brackets, which are not necessary, we can see that we can divide a tangle into 2 subtangles. For example, this KLMN can be divided into tangle KLM and N, and tangle KLM into KL and M, and of course KL into K and L, and it's an ambiguous operation. So here are examples of more and more complicated tangles where I change the representation from summation to multiplication representation. And it can get quite complex, I think. And Conway also introduced his notation to make it simpler, but still amount of this brackets can be overwhelming and hard to read. Therefore, I found it useful to represent these tangles using expression tree notation. So as I said, we can continuously divide each tangle into two subtangles. Each tree has a top on in its left top corner, and it can be divided into its right part and left part, which are just factors of multiplication. For me, it makes reading these tangles simpler. But most importantly, it heavily accents that right and left factors of multiplication are different, yeah, because the left one is rotated and the right one is not rotated. They have different properties, and this notation heavily accents this difference. So we wanted to use this expression tree to, of course, find some way to express a tangle in some unique representation, to which every tangle could be brought to create an invariant. So we could take any algebraic tangle and transform it into a canonical form, and then compare different tangles in their canonical forms. So if they have the same canonical form, we would know that they are the same. But if they have different canonical representation, we would know that they are different. So the tree can be divided indefinitely. So we need to stop somewhere. So our choice is to keep right leaves as integral tangles. So by leaf, I mean a node which is not which doesn't have any children anymore. So in our, after such, if we choose integral tangles to be right leaves, we can use twists to move them around the tree, to move them on the very far right. It can be useful, for example, when we rotate a tangle, because we can always keep this integral tangle still on the right, which is very suitable and useful. For this case, we also introduced a power notation to accent the tangle, which is on the right. And in such notation, after the rotation, this rightmost integral tangle, the right leaf, stays at the same place. So we've chosen what right leaves we want to keep. And in our binary tree, we also need to choose left leaves. So our choose for left leaves is to have rational tangles as them, because we already know that they have great properties. Every rational tangle can be simply represented as a fraction, and we can formulate isotopy preserving moves in terms of these fractions. It may look complicated now, but actually, if you implement a tangle representation as a implement it as a binary tree, then these moves are simple, and many different situations can be treated as one. So the first graph over here is just removal of the left child. The next one is a twist, and the last one is flipe with a twist. And using these operations, they are not enough, but we can now formulate a canonical form of a algebraic tangle. And our canonical form is, as I already said, we want to left leaves have to be a rational tangles, right leaves to be integral tangles, but also we want our left leaves, our rational tangles, to be positive and to have fractions larger than 1, because this form is strict and unique. And we can follow this. We can just flipe and twist such a rational tangle and keep the integral tangles on the right. And additionally, we have some other conditions which follow from our isotopic moves. The way of thinking is, for every isotopy preserving move, there is some freedom, and we want to restrict this freedom. So for every state in which tangle can be moved from state A to state B, we want to force a tangle to be, we decide which of these states we prefer, and the other forbid the other state. So here are these forbidden subtrees of a tangle tree. In our canonical form of tree representation of a tangle. And we've proven that this canonical form is unique. So our outline of our proof is that there is an algorithm which changes a tangle, transforms a tangle into canonical representation. And if we modify this tangle A by any isotopy preserving move, and the output of algorithm is the same, then the canonical representation is unique, yes, because otherwise we would have two canonical representations, they won't be unique. And algorithm is divided into three parts. First part is about removal of left leaves which are not necessary and can be absorbed by some other node. So the tree is traversed using pre-order traversal. So first we go to the left leaves, and if we have no other left, we go to the left children, and if we do not have any left children, then we visit right children. So this part is for, let's say, cleaning the table to be sure that actually every leaf is in a simplest possible representation, like rational tangle, as I shown you on one of the first slides. There was a rational tangle which with few twists looked much simpler. So that's the goal, to make rational tangles simpler and to have smaller tree. The second part is crucial, and as mostly is about flighting, which is the hardest move, let's say. And this part is performed many times. So we traverse the tree. If we find a state which is forbidden, we perform a move, and then start tree traversal from the beginning, from the top. And we perform such operation until there are no possible moves anymore. And then we perform the third part, which is just a simple ring move, which is, I guess, the simplest of these isotopic preserving moves. But it's of course not enough to classify tangles, because we need some input to our algorithm. So we start from generation of alternating tangles up to n crossings just by partitioning an integer. So if we want to classify tangles up to 14 crossings, we take all numbers up to 14 and partition them into all possible nested sequences with positive numbers, but there can be zeros at the end of each nested sequence. And these zeros represent the right leaves of the tangle. These are integral tangles. Then we create non-alternating tangles by changing these zeros into negative numbers. And it's enough to match the number of these negative crossings, match the level of nestedness. Because after some number of these negative crossings, we can transform our tangle into alternating tangle, but with a different sign. And alternating tangle we already generated in the previous part of the algorithm. Then we bring these tangles into a canonical form. For each of these tangles, we derive new tangles by rotations and reflections. to determine their symmetry. Then we choose a representative tangle for each set of tangles created by rotations and reflections, and keep only unique records. This step is to remove tangles which are isotopic. We just want the unique set. We want to reduce number of tangles. And then we want to take these unique tangles and brute force flighting to find representation with minimal number of crossings, because our canonical representation does not necessarily have minimal number of crossings. So this way we increased the classification of tangles from 7 crossings, which was classified by Moriuchi, from 7 crossings to 14 crossings. So from around 136 tangles to 1.9 million tangles. And then we were interested in symmetry of our tangles, because of course we can classify tangles up to isotopy, but someone can say that, okay, if I have this tangle, I can rotate it around X, and it may be not isotopic tangle, but we can easily obtain one from the other. And such tangles related by rotations we call equivalent, and tangles related and set of tangles related by rotations and reflections we call an orbit. So it's enough actually to only have one tangle of each orbit and to know symmetry group of each of these tangles. And this symmetry group can be interesting in itself. So there are 3 operations which are enough to create our rotations and reflections. And here they are presented. It's mu, eta, and mu operations. And naturally, they are generators of the 8 times Z2 group, which is a symmetry group of a square embedded in 3D. So it's a square with 2 sides. So it's the maximal possible symmetry for our tangles, but actually no tangle follows this symmetry. And we can prove it using fraction, but fraction I presented is a fraction of rational tangles. But it can be generalized to algebraic tangles, although it's not a perfect invariant anymore. But we can calculate how fractions change with these rotations and reflection transformations. So some of these operations do not change a fraction. Some of them change fraction into opposite fraction, and some of them invert fraction. So if a fraction is represented by a rational number, and we perform an operation which changes fraction by changing sign and inverting the fraction, its fraction cannot be the same, because if we have the only fraction which does not change after changing the sign is 0, an infinity tangle, 1/0. The only fraction which does not change with inversion is 1 and -1. And if we want to follow both of these conditions, it's just impossible. So it limits possible tangle symmetries.
Sorry to interrupt. It's
Oh,
3 minutes left. Sorry about that. Sorry about that.
okay, you frightened me. Okay, I'm ending.
Sorry.
I need like 2 minutes, 3 minutes. Is it okay? Okay,
Yeah,
fine,
sure,
2 minutes.
definitely.
Okay.
Yeah.
Okay. So if you look at the left, uh, 4 tangles in left top corner, any of them cannot be equal to the tangles in the left bottom corner, and the same on the tangles on the right. So 4 tangles in the right top cannot be, any of them cannot be equal to the right bottom. So we can study subgroups of the Z2 group, and just to look which subgroups are possible for tangles, just by which symmetry groups are possible for tangles, just by removing all these groups which generators are forbidden by our restriction. So it gives us a table of possible symmetry groups. And what's interesting, these groups which are mirror, like which have mirror symmetries, these tangles are much less common. So if you look here at tangles which are from non-mirror symmetry group, I told you there is 1,9 million, around 1,9 million tangles in general. And this number here is similar, but if we look at tangles which have some reflection symmetries, there is less than 500 of them. And what's more interesting, if we divide tangles into X and X type, so strands bar are connected diagonally, or V or H. So V strands are connected vertically, the boundary of the Conway ball, or horizontal. We can see that if there exists a tangle of X type with minimal number of crossings, let's say 9, then there are no tangles of another type which also have a reflection symmetry. I don't know why that's the case, but that's what we found. So now I'm nearly ending. We create a web page server called Tangle Info, where you will be able to check, transform your tangle into a canonical representation and check its symmetry type and look at all tangles from its orbit, and also to filter your tangles based on symmetry or fraction if you wish. And also you would like to publish an article soon about this project. So that's all, and thank you for introducing me to this topic.
Thank you for your very inspiring talk. It was very nice. I would like
Thank
all of
you.
us to you. And now I will stop recording. And do you have